So we're going to get into our first main set of identities now. We're going to talk about both sum and difference identities. So we have them for the cosine function, for the sine function, and also for the tangent function. I'm going to go through and I'm going to start with the cosine, and then I'm also going to show you how to prove one of these, but it is the only one I'm going to prove because otherwise it would take forever to get through them all. So what's going to happen here is if I'm adding maybe two special angles, I don't know how to evaluate necessarily the sum of that angle. Like if I take 60 degrees plus 45, that's 105. I don't know what cosine of 105 degrees is. However, if I can break it down into cosine of 60 and cosine of 45, I do know how to evaluate those. So this is going to help us find the exact value for more special angles. So if I'm taking cosine of alpha plus beta, and also if I'm taking cosine of alpha minus beta, you're going to see these are very similar to each other, but the signs are different, okay? So cosine of alpha plus beta is we're going to take cosine of alpha, multiply it by cosine of beta, and then we're going to subtract sine of alpha times sine of beta, okay? So this is the sum of two angles for cosine. The difference identity is the same. You still take cosine of the first angle, cosine of the second, but now you add sine of the first angle, sine of the second. Okay. So again, same formula, different sign. And the same is going to be true for the sine identities and also for the tangent identities, okay? So what I'm going to do is I'm going to prove the difference, which is the second formula, the difference of two angles. So I'm going to assume that beta is the smaller angle, alpha is the bigger one, because if it's the reverse, it's still going to be the same formula. And what I'm going to do is I'm going to consider a bunch of different points on here. So I'm going to draw a picture as to what's going on. So my first angle, beta, is the small one. So that's going to be this angle here. And then alpha is going to be this bigger angle all the way over here. So this end point on that unit circle would be cosine of this angle, sine of this angle. The second point I'm going to call P2. This is cosine of that angle, sine of that angle, okay? What I'm going to do instead is I'm going to look at the distance between these 2 points, and I'm going to call that D, okay? Forms a nice little triangle, really. What I can also consider is if I take this and I move that so that my starting side right here is on the x-axis. So what I can look at is what is this angle right here, and it would be the same as over here, okay? So this full distance is alpha. If I want this piece, I need to remove beta. So this angle in here would be alpha minus beta, which is that difference that I want, okay? So I'm taking this triangle and I'm moving it so that this side here is on the x-axis, okay? So this angle is exactly alpha minus beta, okay? So then those two key points here, point 1 has been moved to A, which has the coordinates 1, 0, because it's just on the unit circle. And then the second point here would be cosine of this angle, sine of that angle, okay? And again, these are exactly the same triangles. I've just taken this and I've rotated it on that unit circle to be here, okay? So the two triangles are identical. So this distance here would be exactly the same as the distance between these 2 points. These other sides are just a distance of 1 because it's on that unit circle, okay? So what I can say is that the distance between point 1 and point 2 is d. It's exactly the same as the distance between point A and point 3. So it's the same side of those triangles, okay? So I'm going to utilize my distance formula, and really what I can say is my distance squared is equal. So this way I avoid the square roots, okay? So remember our distance formula is the difference in x values squared plus the difference in y values squared underneath a square root. So starting over on this side, if I look at the distance between these 2 points, I take the difference in x values squared. So that would be cosine of alpha minus cosine of beta squared. And then I add the difference in y values squared, which is sine of alpha minus sine of beta. Okay. That equals the distance between these 2 points. So that is my difference in x values squared. So that's cosine of alpha minus beta minus 1 squared plus the difference in y values, which is sine of alpha minus beta minus 0 squared. Okay. So again, the distance formula involves the square root of each of these, but I'm just immediately squaring it to get rid of both of them. Now from here, I'm just going to do a lot of manipulation and eventually get to this formula here. Okay. So unfortunately, I do need to square all of this out, but thankfully at least it's not too terrible. So cosine alpha minus cosine of beta squared will give us cosine squared of alpha minus 2 times their product, so cosine of alpha, cosine of beta, and then plus cosine squared of beta. Same thing with the sine. Put some parentheses around it to make life a little easier to keep track. This gives us sine squared of alpha minus 2 times the product of these, and then plus sine squared of beta. Okay. Doing the same thing on the right-hand side, we're going to get cosine squared of alpha minus beta minus 2 times the product, which is cosine of alpha minus beta times 1, and then plus 1. And then at least thankfully on this piece, sine of alpha minus beta minus 0 is just the sine function. So you end up with sine squared of alpha minus beta. And we can squeeze that in. Okay. So here's where we're going to use a lot of Pythagorean identities. So if I look, I've got cosine squared of alpha plus sine squared of alpha. Those are going to simplify to 1. Okay. Because I can just drop all of these parentheses. Then the minus 2 cosine of alpha, cosine of beta stays untouched. Then I've got cosine squared of beta plus sine squared of beta. That also simplifies to 1. Okay. And then we've got the minus 2 sine of alpha, sine of beta. Okay. So looking good now on that right-hand side. It's cleaned up a lot, and this is looking great because, oh, I forgot my alpha in here. Don't do that. So I've got the cosine of alpha, cosine of beta, sine of alpha, sine of beta, which is what I want. Then on the right-hand side, we've got cosine squared of alpha minus beta. And then I've got sine squared of exactly that same angle. So again, that is a Pythagorean identity that is equal to 1. Okay. And then we've got minus 2 cosine of alpha minus beta and plus 1. All right. So we're looking good. Now we can clean stuff up. We have 1 plus 1. That gives us 2. Minus 2 cosine of alpha, cosine of beta, minus 2 sine of alpha, sine of beta. And then on the right-hand side, 1 plus 1 gives us 2, so we have 2 minus 2 cosine of alpha minus beta. Okay, well, moving the 2 to the other side, if I subtract that, nice things happen because both the 2's end up canceling each other out. So that leaves us with minus 2 cosine of alpha cosine of beta, minus 2 sine of alpha sine of beta equals minus 2 cosine of alpha minus beta. And then going through, I just want to divide everything by negative 2, which is the same thing as timesing by negative 1/2. And that's going to turn all of these to be positive and get rid of all of those 2's. Okay. And that is exactly our difference identity that we stated. Okay. So it shows cosine of alpha minus beta is equal to cosine of alpha times cosine of beta plus sine of alpha sine of beta. So the same idea would hold if you prove any of these other ones. So again, just for time's sake, I'm not going to do that. You're not going to be expected to prove these identities either. They're complicated, but you should be curious about where they come from and why they're true. Okay. Let's instead now turn to see how do I actually utilize these. So I'm going to go ahead and I'm going to find the value of cosine of 105 degrees. So 105 is not a special angle. Really just 90 is, and then the next one after that is 120. So instead I need to see, can I break down 105 into 2 special angles? And indeed I can. You can do this a bunch of different ways, but the way that pops into my brain is 60 degrees plus 45 degrees. You could think of this also as subtraction, but you'd have a little bit more work that you'd have to do to get to that, okay? So now I know how to evaluate cosine of 60 degrees and cosine of 45 degrees, and same thing sine. These are 2 special angles on my unit circle. So utilizing my sum formula, cosine deals with the same functions. So you get cosine of 60, cosine of 45, and then you get sine of 60, sine of 45, but the sine will be the opposite, okay? And then from here, now I know how to evaluate each of these. Cosine of 60 degrees is 1/2, cosine of 45 is root 2 over 2. Sine of 60 is root 3 over 2, and then sine of 45 is root 2 over 2. So simplifying this gives us root 2 over 4, and then this is minus square root of 2 times 3, which gives us minus square root of 6 over 4. And then combining those, because they have the same denominator, the exact value of this is square root of 2 minus square root of 6 over 4, okay? So this is the exact value of this angle. So again, it's hard to do exact for anything other than special angles, but this does give us a way to kind of work with it. Because if you plug this into a calculator, you sure are not going to get this expression. You're going to get a decimal approximation. Okay. So let's now look at the sum and difference identities for the sine function. And again, these have the same format, but different signs. So sine deals with the opposite trig functions being multiplied. just like so katoa. So here we're going to take sine of alpha and times it by cosine of beta. So opposite functions. Then you need to switch those roles. Now I need cosine of the first angle, sine of the second. And then for the sine identity, the sine stays the same. So if I'm subtracting 2, you again get sine of the first angle, cosine of the second. Then I need to switch cosine of the first, sine of the second, and the sine stays the same. Okay. So again, you could evaluate this the same way. If I want to do sine of 105 degrees, you can break it down as 60 plus 45, and then you fill in those pieces into each and evaluate those. What instead I want to work with is finding now sine of 5 pi over 12. Because when we're working in radians, not as straightforward as when we're working in degrees. So what I need to do is I need to break this angle into 2 special angles. So again, that's something dealing with pi over 3, pi over 4, pi over 6, or some multiple of it. Because it could totally be that I'm working with like 3 pi over 4 or 5 pi over 6. I don't know, okay? What I'm going to do is I'm going to find, if I make one be, say, pi over 4, what would the other angle have to be to get me to 5 pi over 12, okay? But since that common denominator is 12, I'm going to pick any 2 angles. It's likely going to deal with a pi over 4, and then the other could be a pi over 6 or a pi over 3, because that common denominator between 4 and 3 would be 12, and then also the common denominator between 4 and 6 would be 12. So this is likely a pi over 3 or pi over 6 combined with a pi over 4. To get the common denominator of 12, okay? So if I pair 4 with 3 or with 6, the common denominator would be 12. So I could say I'm going to have pi over 3 plus something, but I'm going to say, well, definitely there has to be a pi over 4 involved to get 12. So what I want is I want to break 5 pi over 12 into a pi over 4 angle plus something else. So let's call it x. Okay. So this is setting in stone. One of my angles is pi over 4. Let's now figure out what the other angle has to be. So all I need to do is solve for x. Okay. So really subtracting pi over 4 gives me my x value is 5 pi over 12 minus pi over 4. Okay. And then I need to make this a common denominator, so I need to multiply this by 3 over 3. And that gives us 5 pi over 12 minus 3 pi over 12. So that gives me 2 pi over 12 as my special angle. And then that reduces, they're both divisible by 2. So this will give me pi over 6. Okay, don't know what happened to the other side of my x. So what this means is our 5 pi over 12 angle can break down as pi over 4 plus pi over 6. And each of those individual ones I know how to evaluate, okay? And again, you can totally do this a different way. You're just going to end up with different angles. So to kind of show you, if I wanted 5 pi over 12 to be pi over 3 plus something, I would then just solve for x, and I'd get a different special angle that I have to evaluate. So same thing again, subtracting pi over 3. X would be 5 pi over 12 minus pi over 3. And then to combine this, you need to multiply by 4 over 4. And so I'd get 5 pi over 12 minus 4 pi over 12. And if you look at that, well, that didn't end up working out. Pi over 12 is not a special angle. So I'm not able to break 5 pi over 12 as 5 pi over 3 plus something else. So I'd have to try something different, okay? So maybe I wanted it to be, let's say, 5 pi over 6. Okay. I know how to evaluate sine and cosine of 5 pi over 6, so let's see if I can write it with this angle. So same thing again, I would go ahead and I would subtract these two to find the other angle. And then this would need to be multiplied by 2 over 2. So that's 5 pi over 12 minus 10 pi over 12. And if I do that, I end up with negative 5 pi over 12. And again, not a special angle, so I can't break it down that way, which is why using those pi over 6 and pi over 3s aren't good to start with, because I don't know which of them I need. Instead, to get 12, I know I definitely need a pi over 4 in the bottom, so that's going to be my root that I go with. To show you one that does actually work out, let's go ahead and make, let's see if I can get rid of all this. Let's make this 7 pi over 6, okay? So if I want one of my angles to be 7 pi over 6, let's see what x has to equal. So it adds to 5 pi over 12. And so same thing again, I would subtract 7 pi over 6. To find that common denominator, multiply by 2 over 2. So that's 5 pi over 12 minus 14 pi over 12. 5 minus 4 is negative 9, so this is negative 9 pi over 12. And then that does simplify, both are divisible by 3. So you get negative 3 pi over 4. And that is an angle I do know how to work with. So another way I could do this is by saying 5 pi over 12 is 7 pi over 6 minus 3 pi over 4. And then in this case, I would use the difference formula. And then I'd evaluate sine and cosine of each of these. Okay. But again, I like to keep it as simple as possible. So I'm always going to start with just one of those angles in quadrant 1 and see what does it have to equal. Okay. But now that I know how to break down 5 pi over 12, when I want to evaluate sine of this, the inside is exactly the same as pi over 4 plus pi over 6. Okay. Then I'm going to use my sum identity. So I take sine of the first angle, cosine of the second. Then I keep the sign the same, and then I switch. I take cosine of the first angle, sine of the second. Each of those I can go ahead and evaluate. Sine of pi over 4 is root 2 over 2. Pi over 6 is a 30-degree angle, so cosine of pi over 6 is root 3 over 2. Cosine of pi over 4 is 45, so root 2 over 2. And again, pi over 6 is 30 degrees, so sine of pi over 6 is a half. So multiplying these out, multiplying those two radicals gives you root 6 over 4, and this is root 2 over 4. And then we can combine it to a single fraction. This is root 6 plus root 2 over 4 for the exact value of sine of 5 pi over 12. Okay? All right. Let's try another example utilizing these formulas. So given that sine of alpha is 3 over 5, and alpha is in between 0 and pi over 2, cosine of beta is 2 root 5 over 5, and beta is in between negative pi over 2 and 0. We want to find cosine of alpha plus beta. Okay. So again, alpha plus beta, I don't know much about that actual angle. However, I can break this down into cosine of alpha, cosine of beta, and sines of that. So if I look at my formula, when I take cosine of the sum of two angles, you get cosine of alpha, cosine of beta, so the same function. Then you're going to get the opposite sign. And then we get sine of alpha, sine of beta. With what's given to us, we know cosine of beta and we know sine of alpha. I just don't know what these two are just yet. Okay. So I need to find these two in order to get the exact value of cosine of alpha plus beta. So we need to find what cosine of alpha is. And we also need to find sine of beta. Okay. And then I will be good. Now, what these tell us are the quadrants that these angles have to land in. So if I consider alpha between 0 and pi over 2, this is quadrant 1. So when I go to find cosine of alpha, alpha's in quadrant 1, so cosine of alpha is going to be positive. Okay. If I look at the angle beta, negative pi over 2 to 0 is right here. So this is going to be quadrant 4. So when I'm finding sine of beta, it's going to be negative. Because again, I'm in quadrant 4. Okay. So I know that sine alpha is 3/5. So I need to find cosine alpha. You can totally make a triangle if you want. I'm going to go ahead and use our Pythagorean identity for this one. I know cosine squared of an angle plus sine squared of an angle has to equal 1. And so I know sine of the angle is 3/5. So I'm going to square that. And then I can just solve for cosine alpha. So squaring that out gives us 9 over 25. And that's equal to 1. Just to rewrite that, 1 is 25 over 25. So this way I have the same denominator. Then moving that to the other side, cosine squared of alpha is 25 over 25 minus 9 over 25, which is 16 over 25. So I'm going to go ahead and I'm going to take a square root. And again, normally you get a plus or minus, but because I know cosine is positive, I just get the positive case. And so taking the square root of each, cosine of alpha is going to be 4/5. Okay. Now I need to do the same thing and I need to find sine of beta. And I'm given that cosine of beta is 2 root 5 over 5. So again, you can totally go ahead and use your Pythagorean identity, or you can go ahead and you can make a triangle. I do not care which method you use. You can use the same one for finding both of these. You can use different ones. But here's our angle beta. Remember, cosine is c. So this is the adjacent over the hypotenuse. So my adjacent side is 2 root 5. My hypotenuse is 5. And then I need to find what is y equal to, but I know it's negative because I'm in quadrant 4. So using my Pythagorean theorem, my one leg squared plus the other leg squared needs to equal the hypotenuse squared. Well, 2 root 5 squared, you square each, so that gives you 4 times 5 plus y squared equals 25. So 20 plus y squared is equal to 25. Subtracting the 20 gives us y squared is 5. And then we get y equals negative square root of 5. Because again, I'm in quadrant 4. Okay. So this tells me sine of beta is going to be negative square root of 5 over 5. Okay. So now I have everything I need. We have cosine of alpha. We have sine of beta. We can now figure out what cosine of alpha plus beta is. So again, just to refresh on these formulas, you get cosine of the first angle, cosine of the second, different sine, then sine of alpha, sine of beta. Cosine of alpha is what we just found as 4/5. Cosine of beta was given to us. That's 2 root 5 over 5. Okay. Sine of alpha was given. That was 3/5. And sine of beta we just found, which is negative square root of 5 over 5. So now I just need to go through and simplify this. So multiplying these fractions out gives us 8 root 5 over 25. The minus minus turns to plus, so that gives us 3 root 5 over 25. And then from here, they have the same denominator. So this is over 25. And then we have 8 of this radical plus 3 more. So in total, we have 11 of that radical. So cosine of alpha plus beta is exactly equal to 11 root 5 over 25. Okay. All right. So I know this seems like a lot. So again, take your time with this unit. Don't wait until last second. You need to get familiarized with being able to identify which formula you need to use. Get that list, get flashcards together, practice writing them over and over and find those connections that stick in your brain. Okay. We have 2 more sum and difference identities, which are going to be for the tangent functions. So these really just come from the other ones as well. So you technically can derive them, but it is a messy process. These are not something that I typically expect you to remember, but we're definitely going to utilize them. So they have the same formula as well, but the signs are going to vary. So if I'm taking tangent of alpha plus beta, what we get to do is we get to take tangent of each and add them together. So the sign stays the same. The bottom is a little bit funky, so tangent involves a fraction. Its sum identity is involving a fraction. The bottom is going to be 1 minus tangent of alpha times tangent of beta. Okay. The same identity holds for the difference. It's just the signs are the opposite. So when I'm subtracting, you get tangent of alpha minus tangent of beta. And then the bottom turns to positive. So 1 plus tangent of alpha, tangent of beta. Okay. So let's try another example very similar to the last one where we're given sine and cosine of one of our angles and we want to evaluate tangent of alpha minus beta. Okay. So I need to figure out what tangent of alpha is and what tangent of beta is. And they tell us at least what quadrants alpha and beta are in. So we need to find these 2 pieces. We need to find tangent of alpha. And angle alpha is in quadrant 3. So tangent is going to be positive there. And then I also need to find tangent of beta. which that angle is in quadrant 4, so it is going to be negative. Okay. And I'm going to have to find that by using the piece that's given to us. So here we know that sine alpha is negative 3/5. And I want to figure out what tangent of alpha is. So this one, I'll go ahead and I'll utilize just my triangle for it. And if you want to draw it in the correct quadrant, absolutely go for it. But we're in quadrant 3, so our angle is somewhere down here. So alpha would be this full distance around. So sine alpha is negative 3/5. That tells us the y value is negative 3. The hypotenuse is 5. And the only thing we're missing is what is x. So plugging in those pieces, I know that x squared plus y squared is equal to my hypotenuse squared. So that tells me x squared plus 9 is equal to 25. Subtracting the 9 gives us 16. And then taking a square root gives us 4. But because we are in quadrant 3, the x value would be negative there. So now I have my full triangle. This value here is negative 3. And so tangent of alpha is again y over x, or sine over cosine. So my y value is negative 3. My x value is negative 4. So this gives us 3/4. For some reason I can't write today. Don't know why I put a 3 there. My x value is negative 4. Okay. Now I need to find tangent of beta, which this one is in quadrant 4. So I've got my triangle. I don't know exactly where beta lands, but we'll just draw our triangle like this. So beta would be all the way around. And I'm given that cosine of beta is 1/4. So this is my x value over my hypotenuse. This is my y value over the hypotenuse. So here my x value is 1, my hypotenuse is 4, and I need to figure out what does y equal. But it's going to be negative because it's quadrant 4. So that gives me x squared plus y squared is equal to my hypotenuse squared. Well, 4 squared is 16, so subtracting the 1 gives us 15. So my y value is negative square root of 15. So again, we are in quadrant 4, and y is negative there. Okay. So now I can figure out what tangent of beta is, and again, that's y over x. So it's negative square root of 15 over 1, which just gives us negative 15. So again, those match up. Tangent of alpha should be positive. It is. Tangent of beta should be negative, and it is. Okay. So now I am set to figure out what tangent of alpha minus beta is. So utilizing my formula, you get tangent of alpha minus tangent of beta. So the same sign, and then the opposite sign. 1 plus tangent of alpha times tangent of beta. So I need to go through and I need to fill in all of these pieces. Tangent of alpha is 3/4. Tangent of beta is negative square root of 15. And then in the bottom, we get 1 plus 3/4 times negative square root of 15. So cleaning that up, that gives us 3/4 plus square root of 15 And then in the bottom, that gives us 1 minus 3 root 15 over 4. And we really, really, really do not like fractions within fractions. So I'm going to go ahead and wipe that by taking everything in the top and multiplying it by 4. And same thing in the bottom. So 3/4 times 4 gives us 3. And then 4 times root 15 gives us 4 root 15. 1 times 4 is 4. And then when I take that fraction and times it by 4, it ends up canceling out. So we just get the numerator, 3 root 15. So this is our exact value of tangent of alpha minus beta. Okay. All right. So we've done that version. Now let's try doing the opposite, where I'm given something that is expanded and I have zero idea what sine of 25 and cosine of 65 degrees are. Not a special angle in any way, shape, or form. I could sit there and I could plug that into my calculator, but if I want the exact value of something that tells me it's going to simplify nicely and be things I can actually evaluate. So what I need to recognize here is I have sines and cosines being multiplied together, and I have the same angle within each of these. So connecting this to my formula, this I can call sine alpha. So that means this is cosine alpha. 65 I can call my beta, so this would be cosine of beta, and this would be sine of beta. So when I'm adding these and it's the opposite functions being multiplied, that's exactly going to condense with sine. And then I'm taking the sum, so the sine stays the same. This is sine of alpha plus beta. So what I can say is that when I'm taking sine of 25 degrees, cosine of 65 degrees, and adding then the flip, cosine of 25, sine of 65, it really condenses as sine of 25 degrees plus 65 degrees. Well, if you take 25 plus 65, that's just 90 degrees. And I know what 90 degrees is, so sine of that is 1. That's just the positive y-axis. So without having to do all of this nasty work, I'm able to condense this really simple and see this really is just 1. Okay? So this is really beneficial in a lot of real life applications. The sine and cosine function are so essential because of that wave shape and that periodicity to it. So they have a lot of practical applications, and being able to condense stuff helps us a lot. All right, so I've got one last example kind of tying all of this in together now. Given that cosine of alpha is negative 12 over 13 and sine of beta is negative 4/5, and alpha and beta are both in quadrant 3, we're going to find the following. We're going to start by finding sine of alpha plus beta. So again, just going to that formula, we get sine of the first angle, cosine of the second. The sine stays the same, and then I switch. Cosine of the first angle, sine of the second. Okay? I'm told what cosine of alpha is, and I'm told what sine of beta is. So now I need to figure out what sine of alpha and cosine of beta are. So we need to find sine of alpha, which because alpha is in quadrant 3, this is going to be negative. And then likewise, when I go to find cosine of beta, that is in quadrant 3, and all of our trig functions except tangent are negative. I'll do this one both ways. I'll show you using Pythagorean identity and then also doing a triangle. So for sine of alpha, I'm told that cosine of alpha is negative 12 over 13. and this is in quadrant 3. So here is my triangle that's going on, and alpha would be this full angle here. Cosine is x, so that's negative 12 over my hypotenuse, which is 13. So I need to figure out what y is equal to. So using our Pythagorean theorem, negative 12 squared plus y squared equals 13 squared. 12 squared is 144. 13 squared is 169. 169 minus the 144 is 25. Taking a square root gives us 5. And then because we're in quadrant 3, we only have the negative case. So our y value is negative 5. So that tells me sine of alpha is negative 5 over 13. To find cosine of beta, I'm going to use now the opposite. I'm going to do the Pythagorean theorem or Pythagorean identity. So cosine squared of an angle plus sine squared of an angle equals 1. And then we know what sine of beta is. That's negative 4/5. So again, you could totally make a triangle here. You don't have to do it this way. You also can totally use Pythagorean identity for this one. So going through and squaring that gives us positive 16 over 25. And then subtracting that, 1 minus 16 over 25 would be 25 over 25. So really you get 25 minus 16 in the top, which is 9 over 25. So taking a square root, and then we only care about this being negative because we're in quadrant 3. So cosine of beta is negative 3/5. Okay. So I have the two things that I need. I now can go ahead and find sine of alpha plus beta. Keep the formula in view. Sine of alpha is negative 5 over 13. Cosine of beta is negative 3 over 5. Okay. Cosine of alpha is negative 12 over 13. And then cosine of beta, or sine of beta, is going to be negative 4 over 5. So at this point, I'm going to trust you could multiply these together, figure this out. For time's sake, this will simplify to 63 over 65. Okay. So sine of alpha plus beta ends up being a positive quantity. For part B, I'm going to find tangent of alpha plus beta. Save us some time. Already got the formula there for us. Tangent of alpha plus tangent of beta, so same sign, opposite in the bottom. So if I want to find tangent of alpha, you can go back up here and just use the triangle, or you can use that it's sine over cosine, whatever you'd prefer to do. So tangent of alpha is sine of alpha over cosine of alpha. Sine alpha is negative 5 over 13. And then cosine of alpha is negative 12 over 13. The 13s cancel, the minuses cancel. So tangent of alpha is going to be positive 5 over 12. Then tangent of beta is same thing. This is now sine of beta over cosine of beta. So going back up, sine of beta is negative 4 over 5. Cosine of beta is negative 3 over 5. The minus cancels each other out, and you end up with 4/3 because the 5's cancel. And those are the two things I needed. So now I can go ahead and I can find tangent of alpha plus beta. So tangent of alpha is 5 over 12. Tangent of beta is 4 over 3. And then in the bottom, I have 1 minus 5 over 12 times 4 over 3. Well, that bottom does simplify kind of nicely, a little bit at least. So 4 does go into 12 3 times. And then in the top, if I want to write this with the same denominator to simplify, we'd multiply by 4 over 4. So that would give us plus 16 over 12. And then in the bottom, we have 1 minus 5 over 9. So simplifying that, at least the top, I can go ahead and now add. 5 plus 6 gives me 21 over 12. And then in the bottom, 1 minus 5 over 9 would be 4 over 9. So to divide two fractions, we multiply by the reciprocal. So that gives me 21 over 12 times 9 over 4. And then we can do a little simplification. 9 and 12 are both divisible by 3, so that leaves me with 3 over 4. So simplifying this, 21 times 3 is 63, and 4 times 4 gives us 16. So that is the exact value of tangent of alpha plus beta. Okay. Now that I have two pieces of information about alpha plus beta, we can go ahead and we can find the quadrant of this angle. So if you notice, both sine and tangent are positive. So I'm going to find what is the one quadrant where that both happens. So since sine of alpha plus beta is greater than 0, this immediately tells us this angle has to be in quadrant 1 or quadrant 2. Okay, my only possibilities. But then since I know tangent of alpha plus beta also ended up being positive, the only way that could happen is if alpha plus beta is in quadrant 1 or quadrant 3. So in order for both of these to be true, you need that overlap. So that angle has to be in quadrant 1. So this only works because I knew two trig functions and I knew their signs for each of them. If I knew about sine of alpha plus beta and cosecant of alpha plus beta, all I'd be able to do is narrow it down to quadrant 1 or quadrant 2. I wouldn't know for certain. But because I had both of them, I immediately could tell the quadrant using our all students take calculus. Okay? So these are pretty fundamental, especially the sine and cosine sum and difference identities. Really, a lot of our other identities are just going to stem directly from that. So if you can remember those, you'll be able to manipulate and find the other angles as well, or other identities.